Look at case number one, and that's the case that everybody is always starting out in solving these with, so it will not be any different. Case number one, what we're going to derive is the equation called the Cottrell equation. It's a one-dimensional planar diffusion problem, no kinetic effect. So the only real effect on the current flow will be diffusional flow. No migration, no convection. All right. Again, the planar diffusion refers to the fact that we've got essentially an infinitely large electrode, so that the only reasonable direction in which things can diffuse from that infinite plane is towards it or away from it. It can't really diffuse sideways, since it really doesn't make any sense to think about diffusing sideways in the infinite plane. It's all the same in every direction for infinity, so we don't worry about that. Makes it a little bit simpler. We've actually solved the basic equations that we need to do for the Cottrell equation. Remember from just now, we derived the form of the concentration of species O dt, which is the Fick's second law. And we saw that in the Laplace plane was C sub O x bar equal to CO star over S plus a constant. We use B before. I'm writing A here because that's what we have in our notes. Doesn't really make any difference if it's B or A in either case. So constant, our initial concentration over S, or the bulk concentration over S, plus this term which we said required a third boundary condition to evaluate. What's the third boundary condition we're using with the Cottrell equation? Well, we can use the boundary condition that we specified for the Cottrell system, because that says that concentration of O at time equal to 0 is equal to concentration, bulk concentration, I'm trying to think of what I meant by that in my notes. Yeah. So as x approaches infinity. That doesn't make sense to me. Oh well. And then current as a function of time. We saw that equation was equal to the Fick's first law and in the Laplace space we saw this was true d sub 0 to the 1/2, s to the 1/2. Okay, so again, we want to find the value of a. Well, as we said, in the Cottrell equation, we're having the specific case that C sub O at 0 at all times is equal to 0. Again, assuming t is greater than 0. Well, we can take the Laplace transform of that particular case, and we see that condition, and then we see that the concentration of O for S, for all S, is going to be equal to 0. Okay, the basic idea is this. If we have a current potential relationship, we're going to be essentially stepping on to this diffusion limited plateau. And if you think about that, what's happening there is that we've now sufficiently negative of the E0 that the rate of the forward reaction is very rapid, and that means that effectively the concentration at the electrode surface is going to be 0. Okay, because we're very rapidly using up whatever arrives at the electrode is immediately reduced, and so effectively the concentration is 0 at the electrode surface. And it doesn't really matter if we step to here, or we step to here, or we step farther out, the effect would be the same, because at all those places, the concentration at the electrode surface is effectively 0. It's not exactly 0. If you do the math, you'll see it won't be exactly 0, but it's close enough to 0 that it really makes no difference. That would not be the case if we stepped, say, to the middle of the wave. Now we have to consider that the fact that the concentration of O would not be 0, but at least it would be something that we could calculate by the Nernst equation, and practically it would be some effect of kinetics. One other thing to point out is that the Cottrell equation doesn't really require reversible kinetics. For example, we could have a very slow rate of electron transfer. So if we had a very slow rate of electron transfer, the E0 might be here, but the wave might occur well negative of that. And that shifting negative is a consequence of the slow electron transfer rate. But as long as we step sufficiently negative to be on the plateau of that slow electron transfer process, we're still at the point where the rate is fast. So even though it's slow, we still can step to the plateau. So almost every chemical system that is not perturbed by some other chemical reaction that accompanies electron transfer can be put into a Cottrell region. And that's kind of one of the reasons that we always use it. So even slow electron transfers can be studied by the Cottrell theory. Well, we've got the expression for the third boundary condition that we need, that we were missing before. And so if we substitute that into the equation here, this equation, which is what we need, we find that we get the following truth. In other words, A is going to be equal to C0 star. And so plugging those numbers in, and we need now to do the inverse Laplace transform. And that's the good question. What's the value of the inverse transform? Let's first of all go to the current. And since we know the value of A now, we can find that the current is equal to this. Which effectively is equal to the inverse transform of 1 over s to the 1/2, which is equal to pi t to the 1/2. And that's in a table in the back if you want to figure that one out. So putting that in then, we see that the current is equal to NFA C0 star d to the 1/2 power of 0 and over pi to the 1/2 t to the 1/2. Okay, so this is the Cottrell equation. This is an equation I would put in my head and not forget, for at least as long as you're taking exams in electrochemistry. And here. So let's look at that Cottrell equation. We can see a couple properties of it. First of all, the current is predicted to be infinite at time equal to 0, just past time equal to 0. And that's discontinuity in the equation, but that makes sense. As we go to just very short time scales, the current will be very large because the gradient in concentration at the electrode surface will be very large. We start from a very large gradient and go to 0 immediately. The other thing that we see is that the current is predicted to decrease to 0 at infinite times. At long times, that t term becomes, a t to the 1/2 term becomes large, then the current becomes small. And in between 0 and infinity, the current will decrease with a functional form of t to the 1/2 power. So we'll see a decay to the 1/2 power. And so if we look and draw roughly the form of the current time relationship, we would see something like this. I'm not an expert at drawing t to the 1/2 curves, but you get the idea. We'd have some sort of nonlinear curve, and that, of course, would go essentially to infinity according to the graph. Another way people draw it, especially that really illustrates the Cottrell behavior, is to multiply the current times t to the 1/2, and then a graph of I t to the 1/2, I times t to the 1/2 time versus t would give us a straight line, and that straight line would be equal to NFAD to 1/2 over pi to the 1/2. So here are a test that you could almost do for what they call Cottrell behavior, and Cottrell is so common as a system that they refer to it as Cottrellian. You know, you'll say something as Cottrellian behavior or something like that, and that would refer to the fact that behaviors like this, particularly that decay with the t to the 1/2, t to the minus 1/2 relationship, is a Cottrellian type feature, and you'll see that again and again in electrochemistry. That's a very important hallmark of diffusion control problems, is that t to the minus 1/2 behavior. Now, for the concentration equation, that's a little trickier, and in fact, we don't really have the tools yet to do that. I'm just going to write it down, but I'm going to, so we can, if we take the Laplace transform of the concentration expression and take the inverse transform of it, we get a form of the equation like this. And a function called the error function complement, ERFC. And the error function complement is not something you run across every day in things, but it's something we use quite a bit, see quite a bit in electrochemistry for this reason, that it pops up in the Cottrell solution. The error function, you have to kind of, it's not something you can just think about sometimes, but the error function is equal to 1 minus, like that, so that you can think of the error function just being a error function complement. And just for a couple things, that for x equal to 0 or infinity, the error function of x is 0 and 1. All right. So for long times, the concentration at O at all times in solution will go to 0, although much slower than the current goes to 0. what we'll also see when we discuss solutions to electrochemical problems, we often cast these solutions of the problems in dimensionless form. Essentially what we're doing is we're dividing through the current or the concentration by some factor so that the units are canceled out on the resulting expression. And we do that often because we can simplify the plotting. Instead of having to write a family of plots, we can often just write one particular plot that describes the behavior of all the values that we would otherwise run across. So in our case of concentration of O as a function of x and t, if we divide through by the bulk concentration, we now see that the concentration can only vary from 0 to 1 rather than whatever it used to be, which could be any value depending on what concentration we started with. And so concentration is made dimensionless that way, and the error function is dimensionless already. So we get this behavior. And so we look at a plot of the concentration of O over the bulk concentration. Of course, the value would be 1 at all. The maximum value would be 1 at any time. And then if we plot x divided by 2d0t to the 1/2, notice the values. That would be centimeters, typically, over centimeters squared per second, times second to the 1/2 power. So all the terms will cancel out. So again, the x-axis is dimensionless as well in this particular case. And so in that case, we'd always see the same basic plot. A plot essentially of the error function as a function of the parameter inside. Okay. All right. Now, doing this sort of experiment to get the Cottrell equation where we do a potential step onto the plateau is the experiment that we do to get the Cottrell equation is to do the potential step, and they call that experiment chronoamperometry. You'll see in electrochemistry particularly a lot of kind of old-fashioned type words, and this is one of them. Chronoamperometry, you can break it down, chrono meaning time, amperometry meaning measurement of current. So it's time current measurement in the thing. So basically measuring current as a function of time. So often they'll prefix it by saying potential step chronoamperometry. Now, the particular experiment that they're doing to get the Cottrell case is one particular type of potential step chronoamperometry. We can do any type of potential step chronoamperometry. For example, we could step from here to here. Of course, if we did that, there would be essentially zero current flowing, and we would not have the Cottrell equation. We could step from 0 to here. That'd be another potential step chronoamperometry experiment, chronoamps they often say. That again would be an experiment, but it would not give us the Cottrell case. Only, for example, if we step from here to here, would be the Cottrell case valid, because only at that point at the diffusion limited plateau would be getting the particular form of the boundary condition that we require. That is, at the electrode surface, the concentration of O is equal to 0 at all times greater than 0. So chronoamperometry for the Cottrell case is just the same as we've already written. I is equal to NFA, D0 to the 1/2, C0 star, pi to the 1/2, T to the 1/2. Now if we started, this again assumes planar diffusion, no R present, no migration, none of these things, and the particular case where the concentration of O is 0 at the electrode surface. You could easily see how you could derive that for R present initially. In fact, all we do is substitute O for R and put a negative sign there, and that would give us a chronoamperometry for an experiment like this, where we stepped from a reduced species to an oxidized species. So R present initially, not O present initially. Okay, but this is this particular case. Okay. Well, this chronoamperometry experiment is something that we could attempt in our laboratory, but the theory does not accurately predict the behavior in real situations. Only under limited parts of the theory do we get exact correspondence. So let's see where theory and experiment break down. And we'll see a lot of the same things happening throughout the thing. We have a theory, but it really only addresses one particular aspect of the experiment. In this particular case, we're only addressing the diffusional part of the experiment. Disagreement. First of all, there is a potentiostatic and cell RC time constant limitations. What do I mean by that? Well, remember the expression predicts infinite amount of current at 0 times, and so that also predicts very large currents at short times. Our potentiostat, our instrument, may not be able to supply infinite currents. In fact, no potentiostat would be able to supply infinite current, and there's going to be a limit to how much it can supply. So at short times, we'd expect disagreement because our instrument cannot effectively allow large amounts of current to flow. It also may not be able to supply the potential step that's instantaneous. In other words, we're assuming the potential step goes from 0 to the initial to final in 0 time, and that's not obviously going to happen. So at very short times, we'd expect a deviation from the theory because our potentiostat is limiting it. Also, remember we've got in our cell a RC time constant. We've got a resistance and a capacitance at the double layer capacitance and the solution resistance. That resistance and capacitance combination is exactly like a low-pass filter in electronics. So if you built a low-pass filter and you try to apply a step to it, what will happen is that the step will be filtered essentially, and you will get a lower current than you'd expect at short times because of the filtering process. And so, rather than getting the infinite current flow, you're going to get something more like this. This is exaggerated perhaps a little bit, but not too bad. You get, instead of an infinite current, you're going to get a fairly rapid rise and a peak and then a decay for T to the 1/2. But here would be the limitations for the potentiostat and otherwise. Now, depending on a couple things, how good your potentiostat is, and also how small that RC time constant is. We can use small electrodes to make that RC time constant smaller as one solution. Or we can use larger amounts of supporting electrolyte to make the resistance smaller. The recorder may have a nonlinear response. Before computers came around, you'd probably record this on a chart recorder or a XY recorder or a strip chart recorder, and those have a fairly slow response. You can use computers now, but even computers cannot collect data infinitely rapidly, so there would be some delay or some distortion because of the computer collecting data, and so on. The second, these are all sort of together. I had them in my notes as 1, 2, and 3, but they're really all the same same sort of thing. The second thing that we often would observe is charging current. Remember we said that if we step our electrode in a cell, the potential of the electrode, we get a charging current. We actually derive that charging current, and that was a value. So our current at any particular time is going to be equal to I sub c, a function of time, plus I sub f as a function of time. Now this actually works in the Cottrell case, that the charging current and the Faradaic current sum as a linear sum. Yeah, that's not always the case, unfortunately. But in other words, we have charging current and Faradaic current. Remember, I sub c is equal to this expression, E sub a over RU, e to the minus t over RS CD, where R is the solution resistance, C is the double air capacitance. And this obviously has a problem. Now, usually the charging current is a much faster phenomena than the Faradaic current. So the charging current might occur at fairly short times, whereas our Cottrell current might occur at longer times. But at short times, you can see where the charging current may significantly affect our data. What else can we worry about? We can always worry about lots of things. Let me move on. I'll skip past some of the notes to talk about something else first. Another problem would be long time effects, and this is often a problem. Particularly convection. If we have this system, we're letting it go for a long time scale. We've assumed that there's no convection occurring, there's no stirring, and we may not intentionally be stirring the system, but we can expect, for example, vibrations in the solution. The building vibrates, our building does, so it's going to vibrate the cell. That's going to cause the things to be stirred up. Even if you remove the vibration of the building, which you can do, another thing that can happen is you can get density gradients. Let's say this is your electrode here, and you're making O to R at the electrode surface. R may have a different density. In fact, it often does. And so you build up a concentration of R at the electrode surface with a different density, and so we can have a stirring effect due to gravity as that different density material either rises or sinks, and that can cause a stirring effect. Or maybe that process releases some heat, especially if you're doing a very large amount, and that temperature differential can cause a convection. So for times greater than 60 seconds, you often have to worry about convection on time scales. So only if you're really careful can you get good data times greater than 60 seconds on typical systems. One way to help you out, for example, is to make an electrode in the bottom of a long tube. So the electrode completely covers a long tube. That way it keeps the material from diffusing in and out of the system, and it keeps convection down to a minimum. And people have done that. It's kind of something you'd only do if you really needed to get exact Cottrell correspondence. The third effect is what they call a nonlinear effect, nonlinear diffusion effect. Remember, we made the assumption that the electrode is infinitely large. Of course, no electrode is infinitely large. All have some dimension to them. And we've assumed that there's only planar diffusional effects, which makes the assumption that material can only sensibly be thought to move perpendicular to the electrode surface if it's an infinite plane. However, if it's not an infinite plane, at the edges, material can diffuse not only linearly to the surface, but it'll diffuse from around the edges. And you can see that because there's more volume around the edges than there is right over the electrode, that the current that rises from the edges can be larger than the current that comes from the linear diffusion straight down. So what you do is you see an enhanced current because of this nonlinear diffusion. For large electrodes, it's called edge effects. And people say, I saw some edge effect on that Cottrell transient because they're seeing larger currents that show up, particularly at long times. The reason you see it at long times is that at short times, the diffusion field really has not built up to the point where it makes any sensible difference whether that edge effect is occurring or not. So example, if we have an electrode here, at very short times, we're only diffusing a short fraction of the electrode size, but at long times, things are now diffusing much farther away, and now we can think about things happening on the edges. So in fact, sometimes people will use a spherical electrode and still be able to get away with using linear diffusion theory because they only consider very short time scales where, just like us on the surface of the Earth sees it as flat, that diffusional scale is linear. At long times then, like if we went out into space, we would see the Earth as round, and so would, for long times, something diffusing in would see it as round. So nonlinear diffusion happens at long time scales. Also will happen if we make very small electrodes. They're called microelectrodes. And for example, if we make our electrodes that only has a dimension of, say, of 10 microns, it very quickly we'll see these edge effects. In fact, within a second or two, the current will be effectively only that due to the edges and not anything due to the linear diffusion process. And so microelectrodes, sometimes called ultramicroelectrodes, have this effect that you often have to worry about. One thing I should point out in the book that's confusing is that they use the word microelectrodes in a way that's not used so much anymore, particularly in the last 20 years. What happened was when they wrote the book, there was really no such thing, or there was not really a lot of interest in very tiny electrodes that had micron scale sizes. So they used the word microelectrodes to refer to sort of normal electrodes that were used for, say, analysis that might have a dimension of a few centimeters, maybe a millimeter, maybe as much as 5 centimeters or an inch. Those are all called microelectrodes, which was not a very good term for them. But they were distinguishing them from the electrodes that you would use for electrosynthesis or bulk electrolysis or something like that, which would have larger electrode areas, such as in the few square feet for a large synthetic operation, or even a few square centimeters for something else. So the book refers to microelectrodes, anything that's sort of on the centimeter scale and smaller, they call microelectrodes. But actually now, the word microelectrode is often limited to use electrodes that actually have micrometer-sized dimension. So don't make that, don't be confused by the book using the word microelectrodes. So that's another problem with long time scales, is that nonlinear diffusion effect. And don't think that it doesn't happen. It happens very quickly to see, 1% effect, and that may be enough to disturb your experiment. Let's go back to the charging current problem. I guess that was number 2. I wanted to talk about it again. The Cottrell equation uses time, and the time, I as a function of time, will be a linear function of the charging current and the Faradaic current. Like so. One way to get around the intermingling of the charging and the Faradaic current, because they're mixed together as a linear function, and you really don't know directly what the charging current is, typically. Even though there's a theory for it, the theory and actual values of charging current are often significantly different. What you find out is that that's not always the best way to handle that. So one thing that people often do is they change the form of the equation to make it a charge-based equation, and they call that chronocoulometry. So rather than measuring current, they measure charge, and charge time experiments can be generated by taking the integral over the time of the experiment of the current as a function of time. And if you do that, you see that you get results for the charge relationship like so. Or the Cottrell equation for coronal coulometry, the equivalent of the Cottrell equation in coronal coulometry would be Q as a function of time would be 2NF NFA D0 to the 1/2 C0 star T to the 1/2 over pi to the 1/2. And what you get then is a QT time curve like this. But often what you do is you plot your chronocoulometry experiment like so. A guy named Fred Anson first came up with this idea. He said, well, if I plot my charge like so, what do I get? If I plot 0 versus t to the 1/2, or q versus t to the 1/2, the Faradaic current is a straight line with a constant slope. But the charging current will occur at short time scales and add an offset to my system. So by understanding the difference between these two lines, that Q would be the charging current Q. In other words, the difference between that line and that line would be the difference. So essentially, by looking at the intercept of this line, okay, because this would be QC plus QF, this would be if we had no charging current present, and we expect that line to go through 0. But since the charging current happens at short time scales, we'll see a rise in the charge and then an offset from 0 that's due to the charging current. And so what we can do is we can subtract off that charging current directly from the plot, and that makes it easier to deal with the expression. Okay, another related problem is what they call absorption or adsorbed films. It arises from adsorbed material. And what do we mean by adsorbed is that any material that does not arrive at the electrode surface by a diffusional process. For example, if a material is stuck, physically adsorbed to the electrode surface that's electroactive, what we can do is we can see a current will flow when we reduce or oxidize that adsorbed film. Because that adsorbed film isn't diffusing to the electrode surface, that current will flow fairly quickly in the course of the experiment. And actually, the charge for the adsorbed film would be simply equal to NF times the coverage of that film. How many moles per cubic centimeter or square centimeter of that material is adsorbed onto the film. And so, again, that is a short time phenomenon because we don't have to rely on diffusion bringing that material to the interface. It's already stuck to the interface. Immediately that stuff will be oxidized or reduced. So we would get, again, Q time experiments, QT to the 1/2 experiments, something like this, where we'd have, here's our Faradaic response. Could be the response of a charging current effect, and then we'd expect maybe for an adsorbed film, again, that charge or the current flows immediately, and so we would have again an offset from that. So you can get here Q adsorbed and understand the, say for example, the coverage of that film on the electrode surface. And we'll see where that adsorption process becomes more important later on.